video, we're going to go over the definitions, the formulas, and all the good stuff in between about average speed, average velocity, distance, and displacement. Okay, so a big majority of physics is just being able to describe how things move. And so the terms that you see in front of you will help us describe how things move. So let's begin. So the first thing I want to do is start off with a generalized formula for average speed. So speed, in its simplest form, is distance divided by time. Okay, and we're going to go over the nitty-gritty behind this formula, and we're going to also explain this formula a little bit more with a couple of caveats here and there. But speed is what you think it is how fast something moves. But the formula or the generalized definition is distance over time. Okay, so with this idea, let's go over the different terms or the different variables. So S is equal to D over T. So the first one is distance. So distance, it's what you think it is, right? It's how far something moves, or it's like the space in between 2 points. Okay, and so there's nothing really special about the idea of distance except it is a magnitude, okay, or a scalar. And we're going to go into the definition of the magnitude and scalar. But what you need to know about the idea of magnitude and scalar, right, is that it is the absolute value. And when we get into the non-absolute value of distance, it'll be a little bit more clear, okay? So let's go into an example of distance, and the idea of the absolute value will come into play with this example here. So let's start off here at position A. So you're at position A, and you travel to the right, let's say 10 meters. By the way, the units for distance will always be lowercase m for meters. Okay. All right, so we go to the right 10 meters, and we end at position B. Excuse me. So the distance for this first part of the trip would be 10 meters. Now notice here, what I didn't write is the word to the right, or a positive, okay? It's just 10 meters, okay? So this is omitted. All right, now from B, let's say we go down here to position C. And let's say that took about 5 meters. So once again, I'm going to point out what I am omitting or not including is the fact that we went down, or another way to describe down would be with a negative symbol, right? Or another way to do that is like south, right? So the things that I'm putting in the brackets are what we call direction, and that links to the definition of magnitude or the definition of scalar, okay? So magnitude slash scalar does not have direction. And by default, for physics, it means that we're looking at the absolute value. And if you're wondering where that absolute value idea comes from, is this idea of positive or negative, right? Those are missing. All right, so from here, let's say we travel to the left, okay, to position D right here, and let's say we travel 4 meters, okay? So once again, in brackets, I'm showing you what I am omitting or not putting down, which is the direction, okay? So I didn't say I went to the left, right? Usually left is negative, okay? Or I didn't go west, right? So these are all directions. Okay, so with this, the total distance, right? Nothing special here. We would just add them all up. 10 plus 5 plus 4 would be 19 meters. This is the total distance. Okay. However, that number would change if we were not looking at distance, but displacement. But more on that later. But the important idea here is that for distance, you're only looking at the numerical value, no positives and no negatives. Okay. So now that we're on the topic of positives and negatives and directions, oftentimes in physics, we'll describe direction with like up, down, left, right, north, south, east, west. But the general rule of thumb is anything that is positive is up, north, east, right. Okay, anything that has a numerical value is often associated with uh, down, south, west, or left. Okay, and when in doubt, it'll be very explicit and it'll tell you that you are looking at some kind of direction. Okay. All right. So distance is just how like the total amount that you traveled, and it is a absolute value. Okay. Okay, so the other variable that you see in the formula is time, but time is actually a little bit more complicated than we might imagine because we're just so used to time, but it's a pretty difficult concept. And the further we go into our course, we will peel back the layers of time. But until then, we'll just consider time to be time. The only thing that you need to know is that the units for time is seconds. Okay, so now that we had the general definition of speed, let's get into average speed. All right, so average speed is, or you may see it written this way, but in physics we use a lot of what we call subscripts. So it comes after the variable and it's like lower and a little bit smaller. And you are looking for the total distance divided by the elapsed time, okay, or the total time. So, for example, um, if we were to go back to this idea up here, let's say from A to B, it took, I don't know, 2 seconds. And then let's say from B to C, let's say that took, I don't know, 6 seconds. And let's say from C to D, let's say that took 1 second. Okay. So if I were to find the average speed, okay, so if we were looking at the average speed for the trip going from A to C, okay, if our formula is total distance over the elapsed time, going from A to C, the total distance would be 15 meters, and the time would be 8 seconds. We can't leave that in fraction form, so we'll have to reduce that to a decimal form, and that's roughly 1.88 meters per second, right? I always like to round to 2 decimal places. So that's our average speed, okay? But let's say we wanted the average speed for the entire trip, right? So the entire trip, the total distance, we have, what did we say? 19 meters divided by the total time, so that's 2, 8, 12 seconds. And so that will be 19 divided by 12. I'm going to plug that into my calculator, and we get a 1.58 meters per second as my average speed. Okay, so average speed is just your the distance that you traveled for the period of time that you're looking at. All right. Now, when we are taking a look at graphs, okay. So let's say we have a position time graph, right? A position time graph, and we have something like this. All right. So let's say this is the first part of the trip A, and this is the second part of the trip B. We can find the average speed for A and the average speed for B. But what a lot of students want to do is they want to take the average between those two numbers, but you really can't. Okay, and so what you have to do instead is you have to use the definition of average speed, which is the total distance over the total time, um, and just find it out mathematically. So let's actually come up with numerical example here. So let's say this right here, we'll keep it simple for us. This took 4 seconds, and this right here, this took 10 seconds. And when we went from A to B, let's say this position there, that was 5 meters. And let's say here, at that point, this is the 7 meters. So we could find the average speed for parts A and B, and we'll do that, right? So the average speed for A to B, okay, the total distance that we traveled is 5 meters, and the total time that it took was 4 seconds. And so that would be 1.25 meters per second. And the average speed from, I guess, B to, let's just call this C, right? We went from 5 meters to 7 meters, right? So that's total distance of 2 meters, right? So we only traveled 2 meters during this portion right here, right? So this segment here, we only traveled for 2 meters. And that was between 4 seconds and 10 seconds. So the total elapsed time would be 6 seconds. So this would be 0.33 meters per second. Okay, so what we just did is we found the average time for trip A and the average, we found the average speed for trip A and the average speed for trip B. And so the pitfall that a lot of students want to do now is they just want to find the average between 1.25 and 0.33, but we can't. We have to use the formula. So the total average, okay, we went, the total trip took 7 meters, right? We traveled total of 7 meters, and it took a total of 10 seconds. So the average speed would therefore be 0.77 meters per second. And that is how you can find different average speeds for different parts of the graph, and also the total average speed. Now, here's something that you need to know about these graphs. So we know that for a position time graph, right, the ideal slope, we just did the buggy lab, and we said that the slope gives us the velocity, okay? And the idea of velocity is just speed with direction. And so if you have a position time graph like this, or maybe it's like even a distance time graph, what you can then do is instead of finding the slope for A and finding the slope for B, is you can actually, if we know we're looking at, we want to know the average speed for 0 to 10 seconds, all you gotta do is create a line from 0 seconds to 10 seconds, and whatever this slope is would be the average speed. Okay? Just a cool little trick. Well, not even a trick. You need to know this. So I'm going to put a star next to that. This is a important idea. Okay? So if we were to find this slope right there, it would turn out to be 0.77 meters per second. All right, so we just went over average speed and the idea of distance. Now let's do average velocity and displacement. So velocity and displacement is just like speed and distance, except for one huge difference. Velocity is speed with direction. Okay, and anything, so we know that speed is what we call a scalar, and a scalar is anything that's just a magnitude. Okay, and direction is just direction. So scalar plus direction, in the world of math and physics, we call this a vector. Okay, so a vector comprises of two things. A vector has the number, and it has a direction. Okay, and that's what makes it a vector. Okay, it has to have these two requirements, the number itself and the direction. So if we were to just do a couple of examples, uh, if we were to say, okay, I'm traveling if I'm traveling 5 meters per second to the left, okay, the 5 meters per second would be the scalar, and left would be the direction. But 5 meters per second left would therefore be our velocity because direction is part of it. Now, I could also easily write this as negative 5 meters per second, right? Because remember that negative could represent left or west or south. Okay, so the difference is speed would just be the 5 meters per second, but the velocity would be the negative 5 meters per second, or 5 meters per second left. And both of these here are describing essentially the same thing. Okay, so velocity is speed, but with direction. And therefore, you might think, well, is displacement distance with direction? And the short answer is nah, not really. It gets a little bit more complicated than that. Displacement is what we call the shortest distance from start to finish. And in fact, I already showed you the formula for displacement in the Buggy Lab video. Okay, so displacement, or the change in position, is xf minus xo. So as a example, right? Also, let's highlight that, right, or star it or something, because this is a formula. Okay, and you want formulas. Okay, so displacement is the change in position, or the final position minus the initial position. So if we were to have a example here, let's use the first example that we used above here, right? I wonder if I could just lasso that. Let's see. Ooh. Yeah, there we go. All right, so let's lasso that. Let's copy and paste that bad boy down here. There we go. All right, so this was our original trip. This is A, B, C, and this is D. So the displacement, if you remember, our total distance was 1054, was 19 meters, but our displacement, it would not be 19 meters. Our displacement would be the shortest distance from our starting point to the ending point. Okay, and that will look like this. Let's do, let's do rainbow. So from here to there, I think that was a bad choice. Let's do, yeah, there we go. Much better. So whatever that distance is would be our displacement, is wherever you started from and wherever you ended. So this would be the displacement from A to D. And we can figure this out mathematically. So let's try it. Okay. So whenever we are doing displacement math and we are in the X and Y coordinate system, okay, and what I mean by that is anything up and down is considered to be the Y coordinate, and anything side to side or left to right is considered to be the X coordinate system. Okay, the rule of thumb, and this applies to so many other units in physics, is that you can only add Y values with other Y values, and you can only add X values with other X values. Okay, so if I take a look at this, what I'm going to do next is I'm going to find all of my X values first. So this 10 meters here, I'm moving in the lateral or left to right position. So this would be 10, right? But because I'm moving to the right, I'm going to call this positive 10. So in my x-axis, we have a positive 10. And then if we take a look down here, I move to the left 4 meters. So I'm going to write that down as negative 4 meters. So my total x displacement would be 6 meters positive. Okay, so that's as if I only moved, let's do this one, but nice and big. That's as if I just went from here and I only went to the right this amount. Okay, and that amount is what we call just 6 meters right here. This would be 6 meters. Okay, and the way that we figured that out is if we just went 10 meters to the right from A to B, and then 4 meters to the left, it's as if we just went from here to here, because that back and forth motion just kind of like negates itself. And now we have to take a look at the y-axis. Okay, so I'm going to show you all the y-axis values. So we have this 5, and that 5 is going downwards, so that will be negative 5. And I think that's it, right? So our total y displacement is just negative 5 meters. So what that would look like would be something like this. So we go from here, and then we go down negative 5 meters. All right, so to find this actual displacement, what you see before you is a right triangle. Okay, and we have to use the Pythagorean theorem to find the actual displacement. And what I'm going to do is I'm going to try to make this a little bit more clean. So we went to the right 6, we went down negative 5, and we have this right triangle right here, and this dotted line is our actual displacement. Okay, and my arrowhead is pointing down and to the right because that's where I ended up, down and to the right from my starting position. Okay, and so if I were to use the Pythagorean theorem, it will be a squared, so 6 squared plus negative 5 squared is equal to c squared. So this would be 36 plus 25 is equal to c squared. And let's see what we get. So our total displacement would be our 7.81 meters. Okay, so if we compare our displacement to our total distance, which was 19 meters, if we just went from our starting position to the end, right, we traveled a lot less. So that's displacement. Now the important thing about displacement is that direction matters. And so what we can say is 7.81 meters. So we could include an angle to describe the displacement. And that angle would just be whatever this angle would be right here. But just to make it a little bit simpler, I could just say down and to the right. Okay, so now it truly is a vector. It has its direction. All right. So that's the definition of displacement. And so now what we're going to do is we're going to go over the definition of average velocity. Okay, so average velocity, much like our definition of average speed, we'll just be looking at the elapsed distance over, the elapsed displacement over the elapsed time. And this is the definition that we came up with for our buggy lab. So this should be a blast from the past. We've seen this one before. Okay, but it's just good to know that this is the official formula for V average. All right, the last thing I want to do is just do a graphical example with you, because that's how most of our problems will look like in our class. All right, so let's do position here, and we have time here in seconds. Let's say the first part of a trip from here to here, this is A, and then let's do this. Okay, this will be B. So one of the things I want to point out is that because velocity is a vector, the negatives do in fact matter. Okay, so we went towards the negative direction there, and then we'll just do, yeah, that'll be it. All right, and let's just come up with numbers. Let's say this is at time, we'll make it simple for ourselves, 5 seconds. And this right here, this time, once again, we'll make it simple for ourselves. We'll make it 8 seconds. Okay. This starting position here, we'll say that is 2. Okay. And then there, that data point right there, we'll make this 5. Okay. And then this data point down here, or this coordinate, we'll call that x is equal to -6. All right. So here we have our different coordinates for this graph. And so let's find the different velocities for parts A and B, and then let's find the average velocity for the entire trip. So the velocity for part A would be the total displacement over the elapsed time. So we went from 2 meters to 5 meters. And so that would be 5 minus 2. Remember, it's always final minus initial. And that took a total of 5 seconds. So this would be 3/5. So this would be 0.6 meters per second. And remember, this is positive. The velocity for part B, I always like to start off by writing my formula. It makes things very easy to know like where I made my mistake. So my final position would be -6 meters, right? That's down there. That's where I ended up. But I started off at position 5 meters. So it'd be -6 minus 5. And if you're wondering why it's 5, then that's because I started right there at the 5-meter mark. Okay. And once again, this is a position time graph. And the total time that took, we went from 8 seconds is the final time minus 5 seconds, which is the initial time. So it took a total of 3 seconds. And so we get -11 over 3. And I'm going to just plug that into my calculator. And that gives us -3.67 meters per second, right? And that negative is important because velocity has direction. All right, so we found the velocity for A, the average velocity for B. And so if I'm looking for the average velocity for the entire trip, I use the same formula, right? My final position would be -6. Once again, that's that right there. This is the -6. And my initial position right there is 2. So -6 minus 2, because displacement is final minus the initial. And the total time that took was 8 seconds. And lo and behold, wow, -8 divided by 8, this gives us -1 meters per second. Okay, and this is my average velocity. And just like average speed, you can find the average by going from your starting to your ending point right there, right? And whatever this slope is your average velocity between those 2 points. Okay, so if you just connect those 2 dots and you find the slope, and in this case, the slope would be -1 meters per second. That will give you your average velocity. All right. I think that's it. I'll see you next time. We'll get a lot of practice in class with all of these ideas. Bye-bye.